The idea that something like evolution might go on in the brain is not a new one. Many of the people listening to this interview might have heard about a field called neural Darwinism, which was advocated by Gerald Edelman. But if you look at neural Darwinism as it was conceived, it's quite clear that what happens in that system is something like selection on a standing variation, and not bona fide evolution, where you would produce newer and newer variants through many generations on which you could select to get to cumulative adaptations. The picture that the selectionist approach gives on the dynamics of the brain is something like the recipe by Michelangelo to make a statue. The idea is that if you have a piece of marble, then you just have to chip off everything which doesn't belong to the image, and then you have finally a statue. First of all, you have to do it quite well. You have to be a Michelangelo or something like that to do that well. The other thing is that the piece of marble is as fully connected in crystal space as possible. But the brain is not like that. The brain is sparse. The brain is sparse in two ways. One of the ways is that most of the connections that could be between the neurons are not there. That would be jolly impossible simply because of the problem with the space requirement of the wiring. The other interesting thing about the brain is that you have sparse activation on an already sparse substrate. So it really stretches the imagination to argue that in a prefabricated form, as a kind of standing redundant variation from the beginning, you have everything there that is necessary, you just chip away which doesn't belong there. Sure, this kind of process does happen in development, but this is a one-shot game. It's like combinatorial chemistry. You produce many molecules and you fish out those molecules that work. Evolutionary biotechnology doesn't work like that. Evolutionary biotechnology produces, by the classical means of reproduction and generating new and new variation, novel variants, and then you are doing evolutionary hill climbing. So the question is whether this kind of process could happen in the brain, although we know that neurons on the whole don't reproduce. That was probably one of the impediments why people didn't think in terms of a bona fide Darwinian mechanism in the brain, although it could be welcome, because we know from biological evolution that it has produced spectacular cumulative adaptations across the generations, and in the brain the generation time could be measured in principle on the scale of milliseconds. So there would be enough time in the brain. If you think about the development of language in children, which takes easily several years, or if you think about the development of something like a scientific theory such as general relativity, which took 10 years for Einstein to develop, or if you want to solve an insight problem, such as, for example, you have 9 dots and you have to connect by a pencil the dots with 4 straight lines without lifting the pencil from the paper. If you want to solve these things, in several cases you will find that you need a lot of time. Apparently you need a lot of unconscious processing, because in many cases the solution pops into consciousness, as it were, without any prior warning. We know that also sleep promotes insight. So the question is, what kind of parallel, possibly Darwinian search could go on in the brain when you are facing challenging cognitive tasks that require days, months, or years, perhaps even a decade. And the InSight project, also called Darwinian neurodynamics, to distinguish it from neural Darwinism, investigates exactly that. What are the possibilities for real evolution to go in the brain, and what it could provide for the understanding of complex problem solving. Another motivation for the project was the finding that is now becoming better and better known, that there is structural plasticity in the brain, which means that in real time, even in adult animals, synapses get eradicated and new synapses are being formed. So it's different from the one-shot game of Edelman and Sanger that I mentioned, that happens during development, overproduction and pruning away, which is not necessary. But structural plasticity means that there is an ongoing process, and Kierkegaard, an experimental neuroscientist, already calls this a Darwinian type of process. So that was another motivation behind the InSight project. Such a process cannot be there for nothing. It's very costly in time and energy, and this wouldn't happen in the brain unless it serves some critical function. So the project would like to understand whether Darwinian dynamics happens in the brain, and what it, if it does, what it can bring to understanding of brain function. Let me also mention a very important analogy, and this analogy is the adaptive immune system. The adaptive immune system happens in the vertebrates. It's adaptive because the antibodies are being produced against the antigens as a challenge, and we know that there is a certain kind of generative grammar there. The generative grammar means that there are component processes such as somatic recombination and hypermutation, and then there is clonal selection for the best binding antibody, which is very important, and this is a really Darwinian mechanism, and it actually originated twice. There is one case for the jawless fish, and there is another case for everybody. The details are different, therefore we know that they are independent, and there is memory in the immune system and so on. So this already suggests that it's not absolutely ad hoc or unheard of to assume that evolution, so to speak, can reinvent itself. It happened for the immune system twice. It may have happened also for the brain. The InSight project would like to investigate, by the collaboration of the various groups, how far this idea holds water. So the Parmenides Foundation in Munich is investigating the conceptual foundations and also doing experiments on InSight. Queen Mary in London was a former partner, but our friend and colleague Crisante Fernando went to work with DeepMind at Google, so Queen Mary is out, but the legacy of Chris Fernando is still with us. At Sussex, Phil Husbands is conducting some theoretical investigations, and Kevin Staras is guiding the experimental investigations, whether some component processes that we suggested that could act like neuronal replication without the neurons themselves replicating, which means, for example, the replication of connectivity patterns could take place. So that is being investigated in Sussex. In Barcelona, the Pompeu Fabra University, Luc Steels is investigating the links between Darwinian neurodynamics and what he calls fluid construction grammar, and in fact fluid construction grammar was one of the teasers in this game, because more than 10 years ago, Lickstairs and me identified the potential link between the two ideas, because many of the component processes assumed are very similar. And Dario Floriano in Lausanne at the APFL, he is applying some of these ideas for robotics. So these are the basic research channels that we are investigating. But undoubtedly, at the heart is the mechanism that we wish to identify, which allows an evolution process to run in the brain. The implications could be potentially far-reaching. I mean, on the basic and theoretical side, we could have a very interesting twist. The interesting twist could be that the evolutionary process is much more powerful in the brain than in the wild. Now this might sound strange, but if you think about it, there are several constraints on how an evolutionary algorithm, as it were, could be run in the wild, what kind of mutations are allowed there, whereas in the brain, using other mechanisms, known mechanisms from neurobiology, there are solutions that otherwise are not available for natural selection in the wild. For example, a very important component, as we have already analyzed, is that in the brain, the mutation matrix can be modified by learning, which means that the productionist variation could be much more guided than out in the wild. This can and could give tremendous algorithmic advantages, but this is just one example of this unexpected empowerment of a basically Darwinian process in the brain. On the applied side, we believe that this project ultimately will lead to the development of smarter machines, but also we strongly believe that if the principles and the details work out, then it will help us to facilitate cognitive excellence in people, have a better approach to teaching, guiding, problem solving, and so on. Thank you.